Welcome and thank you for joining us for today's webcast, Thermal Management Solutions for Directed Energy Applications, sponsored by Advanced Cooling Technologies and TechBriefs Media Group. I'm Billy Hurley, Associate Editor with TechBriefs Media Group, and I'll be your moderator today. Our webcast will last approximately 30 minutes, and there will be a question and answer period at the end of the presentation. If you have a question, you may submit it at any time during the presentation by entering it in the box at the bottom of your screen. Our presenters will answer as many questions as possible at the conclusion of the presentation. Those questions not addressed during the live event will be answered after the webcast. Also, twice during the presentation today, we will present you with a poll question, which we invite you to answer at the appropriate time. In order to view the presentation properly, please disable any pop-up blockers you may have on your browser. At this time, I'd like to introduce our speakers. Pete Ritt is Vice President of Sales and Marketing for Advanced Cooling Technologies. Pete joined Advanced Cooling Technologies in 2010 to head the company's technical services business. During this time, the group has successfully provided thermal consulting, design, and prototyping solutions to commercial customers in the lighting, renewable energy, industrial equipment, and medical industries. Also on the line today for our live Q&A is Dan Fritsch. Dan Fritsch is a product development engineer in the Defense and Aerospace Product Development Group. At ACT, he has designed and built a number of custom thermal management products and systems. Dan has experience with heat pipes, liquid cold plates, pumped liquid systems, and pumped two-phase systems. Prior to joining ACT, he designed and built a pumped two-phase system as part of his research for the Laboratory for Advanced Thermal and Fluid Systems at Villanova University. So, now I'd like to hand the webcast over to our first speaker today, Pete Ritt. Pete?
Thank you, Billy. I'm Pete Ritt, and along with Dan Fritsch, we are delighted to be with you today. Directed energy applications are receiving more and more attention every day. These products are showing great promise in military and in directed energy weapons, DEW. With the growing desire to make these devices more powerful and more mobile, there is also a growing need to have a thermal management solution that is high performance with reduced footprint requirements. In today's webinar, we'll review the basics of a thermal management solution for directed energy applications and then go into a little more detail of two specific thermal management solutions: phase change materials for temporary heat storage and pump two-phase cooling for high heat flux, low space claim requirements that are enabling these directed energy applications. Directed energy weapons, DEW concepts, have been around for a long time. As we can see here, ancient mariners envisioned using the sun as a military weapon. But only recently have we advanced to building and testing operational prototypes. The desire to make these devices more powerful and more portable has required the development of thermal management technologies that are more space and energy efficient. As mentioned previously, today's webinar will focus on two technologies that are at the forefront of DEW thermal management: PCM Heat Exchangers and pump two-phase cooling. An established solution for thermal management for mobile DEWs is to have a three-circuit heat exchanger system consisting of the following elements. 1. A primary laser cooling loop, seen as red as the coolant. Temporary thermal storage, PCM as seen in gray. Heat rejection loop, seen as blue as the refrigerant. The primary laser cooling loop is frequently defined by the laser manufacturer to ensure the safe and reliable operation of the laser device. These loops are typically liquid-cooled. The temporary thermal storage section absorbs waste heat during the on cycle and dissipates it during the off. The heat rejection loop removes the waste heat and delivers it to the ultimate heat sink. These have typically been either vapor compression systems or liquid cooling. The focus of today's webinar will be PCM heat exchangers and heat sinks, which are being used in DEW solutions, but have other potential applications, and pump two-phase cooling, which offers the potential to improve the performance of both the heat rejection system through simplified controls and the primary cooling loop through improved isothermality across the laser surface, as well as other high heat flux, space-constrained applications. Here is a more detailed schematic of the three-circuit heat exchanger system. To help with the thermal storage function, there are in many cases thin layers of PCM sandwiched in between parallel flows of both the deionized water and the refrigerant. The vapor compression system operates continuously, but is only sized for average heat load, since the PCM balances the peak load from the DI water loop. These layers can be added as needed, depending on the PCM volume requirements. So what's the benefit? ACT determined the performance difference for a system operating around a 33% duty cycle with and without a PCM circuit. This analysis used off-the-shelf components outside of the PCM heat exchanger. As you can see on the table on the bottom right, the weight of the compressor and condenser are significantly reduced. And although additional weight of the PCM and enclosure mass to the heat exchanger portion was included, there is an overall weight reduction of 54%, which is quite significant. Now let's turn it back to Billy for a polling question.
Thanks, Pete. Now it's time for our first poll question today. It will appear on your screen now. And the question is, does your company currently utilize or are you considering using heat pipes, high K plates, or vapor chambers in your products? And your choices are yes, we use them now. Choice B, considering using them in the next 0 to 6 months. Choice C, considering using them in the next 6 to 12 months. Or D, you have no current plans to use them. So you can make your choice by selecting the appropriate button on your screen. Again, does your company currently utilize or are you considering using heat pipes, high K plates, or vapor chambers in your products? And as you make your selection, I will hand the presentation back over to Pete Ritt. Pete?
Thanks, Billy. Both PCM heat exchanger and heat sinks for temporary thermal storage and pump two-phase cooling are emerging thermal technologies which have applications both within and outside of directed energy application. Let's now explore both of these technologies in more detail. To begin, we'll start with PCM. As is probably obvious by the name, PCMs operate using a phase change, in most cases solid to liquid phase transition. During the phase transition, a material's latent heat increases dramatically, which allows it to store thermal energy for a finite period of time. The major benefit of integrating PCMs is that it will maintain its melting temperature during the phase transition. Depending on how much PCM is in the system and the power being applied to it, the heat exchanger or heat sink storage capacity can be a couple of seconds to several minutes to even a few hours. We'll investigate PCM in a little more detail, exploring some design considerations and a few PCM heat sink applications. The key attributes of phase change materials is the latent heat of fusion, which is the heat or energy that is absorbed by a material during the melting process. Phase change materials typically can absorb orders of magnitude more heat than single-phase materials. The graph on the right helps to explain this effect. Temperature is plotted on one axis, heat, Q, is plotted on the other. The red line is a plot of sensible heat, that being heat that causes a direct temperature change. The blue line shows the performance of phase change material. When the PCM reaches its melting point, it maintains a constant temperature, as seen in the blue shaded area. It maintains that temperature until all of the PCM is melted, when it will return to the sensible heat regime. Note the sharp temperature transition is a function of PCM purity. This effect has many benefits, the most important of which is temporary heat storage. These solutions can help reduce weight of large metal heat sinks, are compatible with many common materials, functions reliably over many heating and cooling cycles, and is completely passive, requiring no moving parts. Some challenges that need to be addressed are the very low thermal conductivity of these materials and the relatively high cost of high-purity, long-chain hydrocarbons. Lower cost, lower purity materials are also available. Let's first consider a PCM heat exchanger. Like with the heatsink, addition of PCM can enable sizing of the heat exchanger to be based on the average power rather than the peak power. The concept here is that the PCM exchanges heat with both a heat source and a cooling loop that is tied directly to the ultimate heat sink. PCM temporarily stores the thermal energy and slowly releases it to the ultimate heat sink. In this way, the PCM can dampen the maximum overall temperature, offering the opportunity to reduce the size of the heat exchanger and likely increase the life of the heat source. The ultimate heat sink can then be reduced in size and weight regardless of what type of system. Some examples include reducing radiator size in space applications and reducing convection heat sink volume in terrestrial ones. In designing a PCM heat exchanger or heat sink, of course, a critical parameter is the selection of the PCM itself. The key attribute is selection of a PCM that has a melting point at the temperature that is acceptable for the device operation. You can see on the chart on the right a series of materials and temperature ranges from plus ice. Several options are available. Other important parameters include compatibility with the base heat sink material, the type of PCM, its purity, and heat storage capacity. Once potential materials have been identified, they should be evaluated for storage capacity, including fin thickness, required PCM volume, and weight. In the table at the bottom, for example, 3 PCMs with the same melting point and fin volume deliver 3 different heat storage performance due to different latent heat and mass properties. Let's now look at the design of a PCM heatsink. In the first step of the design, power and thermal storage time targets are used to determine the volume of the PCM required. From there, 2 primary challenges arise associated with the design of a PCM module. The first is designing around the poor thermal conductivity of PCM. Wax-based PCM have thermal conductivities between 0.2 and 0.3 watt per meter Kelvin. Simply filling a container with PCM and applying a heat load would create a large temperature rise as the PCM melts. The second challenge is managing the voids at the location of critical heat loads. You can see in the figure on the right, a void volume is present to allow for expansion of the PCM during phase transition. In most cases, where orientation with respect to gravity varies, the location of the PCM when it melts and freezes will vary as well. If there is a significant empty space around a critical component, that component can see a large temperature rise before the PCM absorbs the heat load. The solution to both of these challenges is in the design of the internal conduction paths, which typically are fins internal to the heatsink. As you can see, conduction will play a large role in assuring the PCM melts without significant temperature rise. The fin spacing, or fin pitch, and thickness of the fins are critical design considerations that need to be addressed. Here is an example of a typical PCM application. In this case, after selecting the PCM, determining the required volume, and designing the enclosure with proper fin and wall structure, it's time to manufacture and test the PCM. This slide shows a tested sample with the estimated properties shown to the left. Note the large changes in specific heat for the different temperatures. Specific heat, which is related to the latent heat of fusion mentioned previously, is the amount of heat per unit mass required to raise the temperature of a material by 1 degree C. The reason why PCMs are so effective is that during phase transition, there is a dramatic increase in specific heat. As you can see, there is an order of magnitude increase from approximately 1,600 joule per kilogram degree Kelvin as a solid to over 60,000 at its melting point between 72.2 and 75.9 degrees Celsius. Here are the results from the test setup we saw on the previous page. As indicated by the solid black line at the top of this graph, we applied slightly over 40 watts of total power with air at room temperature. If you're familiar with PCM, you've probably seen the blue theoretical line. Basically, the module heats up until it reaches the PCM melt temperature. It can then hold within a few degrees of that temperature until nearly 100% of the PCM has melted. Once all the PCM is melted, the temperature begins to rise at the rate dictated by the specific heat. In this case, the PCM heatsink was designed to absorb the latent heat load for about 250 seconds with some margin. The red tested results match fairly well, and the theoretical temperature was never exceeded. And now we'll turn it back to Billy for our final polling question.
Thank you, Pete. It's time for our second and final poll question. It will appear on your screen now. And the question is, when looking for thermal management solutions, what is the single most important criteria your company uses to make their decision? The choices are A, cost, B, performance, or C, reliability. So you can make your choice by selecting the appropriate button on your screen. Again, what is the single most important criteria your company uses when looking for thermal management solutions? So as you make your selection, I will hand the presentation once again back over to Pete Ritt. Pete?
Thanks, Billy. Now let's take a look at an example of a PCM heat sink. This application is for electronics thermal management. An exploded view of these types of heat sinks is seen on the right. The red metal parts encompass the enclosure in which the PCM and folded fin assembly are located. The block diagram details the key elements of the device. First, the transient heat load, power, and time are established. This determines the required PCM reservoir sizing. There is then the iterative design sequence, reviewing fin design and structural analysis that ultimately results in the final design. This transient thermal modeling will confirm the heat transfer to and from the PCM, identify the location of the PCM melt front over time to ensure adequate PCM is present to handle the full transient load, and the overall system delta T to make sure the devices are not overheating. A second PCM heatsink application is far smaller than the directed energy applications we discussed initially. Many semiconductor communication devices operate in a transient on-off mode. During the on cycle, they utilize a lot of power and the devices can get quite hot. Fortunately, duty cycles are relatively short, typically between 2 and 10%. Locating PCM near the individual gates can aid in increasing performance reliability and extending life of these devices. As can be seen in the schematic on the right, the pulsed heat source is on a GaN layer and a silicon substrate. PCM is embedded within the silicon substrate, and when the device is on, the heat will cause the PCM to melt. As we have seen, the melting provides some stability in temperature, and so very high temperatures from repeat cycles are avoided. In these applications, ensuring the proper amount of PCM, enough to absorb all of the heat during the on cycle, while also being able to dissipate all of the heat in the off cycle is important. Part of the system design should include calculation of the minimum distance between the heat source and the PCM to avoid parasitic effects. The key takeaways from this portion of the webinar is that phase change material heat exchangers and heat sinks can be used as an effective way to temporarily store thermal energy. This technology has many benefits, including a totally passive solution, redundant thermal management, as well as the opportunity to reduce the overall size of the heat sink or heat exchanger. We reviewed some of the basic PCM material and heat sink design considerations. PCM selection and volume is dependent on the component operating and boundary conditions, primarily power and time. These parameters are well known and can be determined quite accurately for those skilled in the art. Also, the internal design of these systems is critical to their performance. The two important design considerations are proper conduction path to and from the PCM to address the poor thermal conductivity of the PCM itself, and designing the module for appropriate internal pressure. Again, those issues are well known and can be addressed. We also provided some examples of using PCM for temporary thermal storage outside of directed energy applications, all with different thermal storage requirements. We discussed applications requiring very low power on-chip devices, medium power electronics cooling, as well as high power heat exchangers for directed energy applications. Undoubtedly, there are many more, and fortunately, with the growing acceptance of this technology, there is also a growing expertise into how to implement them. The second thermal technology that we like to review with you today is pump two-phase cooling. This is a high-performance, low-space claim thermal solution that is finding its way in directed energy and many other high-power applications. We'll provide a technology overview, a comparison with the more traditional liquid single-phase cooling, and then examine some of the benefits this emerging thermal technology can offer. Let's start with an explanation of the technology. P2P systems are designed such as the working fluid enters the heat source. It is close to its saturation temperature. When the working fluid comes across the evaporator surface, boiling occurs, and the latent heat that is absorbed by this phase change is used to remove waste heat from the evaporator. This thermal management solution is much more efficient than traditional pumped liquid systems. To examine the benefits of pumped two-phase cooling, it might be beneficial to review the basics of traditional pumped liquid single-phase cooling. In these systems, a chilled liquid is pumped through tubing or a manifold that is in direct contact with the heat source. The main components are the cold plate, a pump, a liquid reservoir, the evaporator or heat source, and the heat exchanger or chiller. These systems can typically dissipate 10 to 20 watts per centimeter squared, but are often defined by the size of the pump. Working fluids are commonly water, ethylene glycol mixtures, or refrigerants. As can be seen in the schematic below, pump two-phase cooling utilizes the same basic components as the single-phase pump cooling system we just discussed: a heat exchanger, reservoir, pump, and a cold plate evaporator. A key difference is that in P2P, a liquid near saturation is pumped into the evaporator where it starts to boil, cooling the electronics and absorbing and removing the waste heat via latent heat of vaporization. So what are the benefits of pump two-phase cooling, especially compared to pump single-phase cooling? First, it requires lower pumping power. A smaller pump means less energy consumption. We'll look at some numbers that support that in the following slide. P2P also uses lower flow rates, which can reduce erosion. Pump two-phase cooling offers a higher degree of isothermality. If we can maintain boiling across the evaporator surface, we can also maintain a uniform temperature there. Additionally, it has higher heat flux capabilities. 300 up to even 1,000 watts per centimeter squared results have been reported. It has good transient response capabilities. We'll show a video of that too, and the simplified control system. Although P2P systems can use water or ethylene glycol, most often they use refrigerant. These fluids are dielectric and ensure there are no shorts via leaks in the system. To give a clearer sense of the flow rate and pumping power differences between pump liquid and pump two-phase systems, the following comparison is provided for an avionics application. In order to dissipate 80 kilowatts of heat, a pumped liquid system using PAO as the working fluid would require a flow rate of 35 gallons per minute and approximately 5.3 kilowatts of power. A pump two-phase system using R245FA would require only 6 gallons a minute and 250 watts of power, which is an 80% reduction in flow rate requirements and a 95% reduction in power requirements compared to a pump liquid system. A significant difference for sure. A common question about pump two-phase cooling is how does it work handling transient heat loads with multiple evaporators? In this video, four parallel evaporators are present and are somewhat randomly turned on and off. When a heat load is being applied to an evaporator, a colored circle is present, and one can see the bubbles exiting the two-phase heat transfer from the top. When no heat is being applied, there is no colored circle and single-phase cooling regime is present. The second heater from the right, with the yellow dot, is the one most frequently turned on and off. There is no audio in this video, but the difference between the pump single and pump two-phase cooling is pretty apparent. Let's now go to the video. Pretty impressive demonstration. In summary, pump two-phase is an active cooling technique that utilizes energy from the boiling of the working fluid to efficiently remove high levels of waste heat. Two-phase heat transfer enables lower flow rate, reduction in system size relative to many pump single-phase solutions, reduction in power consumption, higher heat flux removal capability, and increased isothermality across the heat source surface. In today's webinar, we reviewed the fundamentals of a three-circuit heat exchanger that is used in many directed energy applications to collect, store, and dissipate waste heat from the on cycle. We then reviewed in more detail two emerging technologies, PCM heat storage and pump two-phase cooling, that are being used to advance these directed energy thermal management solutions. PCM is used to passively collect and store waste heat so that it can be dissipated during the off cycle. Pump two-phase cooling is a high-performance active cooling system that utilizes latent heat of vaporization to efficiently remove large amounts of waste heat. These two thermal technologies are finding many applications both within and outside of directed energy applications, some of which were reviewed today. We thank you for your time, and now we'll turn it back to Billy for some questions.
Thank you, Pete. At this time, we'd like to begin our Q&A. If you have a question, you can submit it by entering it in the box to the left of your screen. And I'd like to welcome Dan Fritsch, Product Development Engineer in the Defense and Aerospace Product Development Group at ACT. Dan, we have some questions here. The first question, why would I want to use a pumped two-phase system instead of a vapor compression system?
In general, a pump two-phase system requires less maintenance than a vapor compression system. A liquid pump is much less complicated than a compressor and has fewer moving components, as well as a smaller physical footprint with the same cooling capacity. It's also much easier to service if necessary. The pump two-phase system does not require oil like a vapor compression system and does not require complex tubing assemblies to be able to return oil back to the compressor. Another reason that we would want to use pump two-phase rather than a vapor compression system would be the isothermality of the system. So typically with a evaporating fluid, you would have higher heat transfer coefficients towards the 0 to 40% quality, thermodynamic quality range than in the latter portions of the quality, where a VCS system has to go through full vaporization so that we can get a superheated vapor at the exit and return that to the compressor for compressing purely gas. A pump two-phase system only operates in the quality range between 0 and 40%, so we keep it in a fairly constant heat transfer range and maintain a nearly uniform evaporator surface temperature. This also allows for much better hotspot management than in a VCS due to the fact that all over the evaporator surface will have similar heat transfer coefficients that will be strictly based on the heat fluxes applied to them at a particular spot. Rather than a VCS, we may have qualities up in the upper range between 80% and 100%, which have much lower heat transfer coefficients and can end up causing much higher temperatures at the evaporator surface.
Dan, can a pumped two-phase system have multiple evaporators?
I think we went over this a little bit in the presentation, but just to reiterate, a pump two-phase system can have multiple series or parallel evaporators. Series evaporators are typically easier to handle due to the fact that we don't need to restrict flow to each one in parallel. Typically, with parallel evaporators, the only issue we can find is caused by flow instabilities caused due to boiling. These flow instabilities cause maldistribution of flow between different parallel evaporators, which can be overcome due to basic single-phase manifolding techniques. series evaporators don't have to deal with this manifolding problem and therefore are a little bit easier to deal with, but can have higher pressure drops and associated flow through a single line.
What components are necessary for a pumped two-phase system?
For a pump two-phase system, it definitely needs to have a liquid pump, an evaporator or a cold plate, a condenser, and a fluid reservoir that could either be a two-phase fluid reservoir or a pressurized reservoir with either a bladder or a bellows-type accumulator.
Yeah, what are the most important design parameters for a PCM heat exchanger?
In general, the main design parameters that we need to take care of when considering a PCM heat exchanger would be the low thermal conductivity of the PCM itself, which can be overcome by installing extended surfaces or fins inside of the heat exchanger to reduce the conduction length between the surface of the PCM heat exchanger, heated surface, and the center of the PCM, as well as the sizing of the actual enclosure of the PCM. We need to make sure that when we size the enclosure that it can handle the entire volume of a heated liquid PCM, since we are essentially melting all of the PCM and then probably adding a little bit more heat to it. We need to be able to handle the full capacity at the highest known temperature.
Dan, this will be our last question today. Why would I use pumped two-phase over a pumped liquid system?
Pumped two-phase offers many benefits over a pumped liquid system. A few of the reasons that we would want to use it would be for tight temperature control over one or several high heat flux components on a cold plate surface. In a pumped liquid system, you'll end up with hot spots towards the exit of the cold plate due to the increase in temperature of the fluid itself. Pumping power is also significantly reduced with a pumped two-phase system for the same cooling capacity, and the cold plates can still be less complicated, similar or exactly the same as a single-phase cold plate, but still provide much better heat transfer and temperature uniformity when using pump two-phase rather than single-phase.
All right, thank you, Dan. That concludes today's webcast. Again, if we did not get a chance to answer your question today, our sponsors will do their best to address them after today's presentation. So our thanks again to Pete Ritt, Dan Fritsch, and everyone out there for joining us. And just a reminder, this webcast will be available on demand at www.techbriefs.com for the next 12 months. Have a great day.